Welcome to today's class on vector analysis. Today we discuss critical point and saddle point. First we define critical point, an interior point of the domain of a function f of xy where both fx and fy, that is partial derivative of f with respect to x and partial derivative of f with respect to y are 0, or one or both of fx and fy do not exist, is called a critical point of f. Now we define saddle point. A differentiable function f of xy has a saddle point at a critical point AB if in every open disk centered at AB there are domain points xy where f of xy is greater than f of AB and domain points xy where f of xy less than f of AB. The corresponding point A, B, f of AB on the surface z is equal to f of xy is called a saddle point of the surface z is equal to f of xy. For example, you can consider the following surface. So first you observe that 0, 0 is a critical point. So 0, 0 is a critical point since f of xy equal to y square minus y raised to 4 minus x square implies fx is equal to minus 2x and fy is 2y minus 4y cube. Now fx equal to 0 implies minus 2x equal to 0. So this implies x equal to 0. And fy equal to 0 implies 2y minus 4y cube. This is equal to 0. So this implies y into 2 minus 4y square equal to 0. So this implies y equal to 0 or 2 minus 4y square equal to 0. That is, now 2 minus 4y square equal to 0 implies 2 is equal to 4y square, or this implies y square equal to 2 by 4, that is 1 by 2. So this implies y is equal to plus or minus square root of 1 by 2. Therefore, the critical points are 0, 0, 0, square root of 1 by 2 and 0 minus square root of 1 by 2. So from this we can observe that 0, 0 is a critical point. For 0, 0 is one of the critical points. So we have f of 0, 0 is 0 square minus 0 raised to 4 minus 0 square, because x and y are 0. So this is equal to 0. Now we show that 0, 0, f of 0, 0 is a saddle point on the surface z is equal to y square minus y raised to 4 minus x square. Here origin is a saddle point because in the neighborhood of origin there are points at which y square minus y raised to 4 minus x square is less than 0, and there are points near 0, 0 at which y square minus y raised to 4 minus x square is greater than 0. So here f of xy is y square minus y raised to 4 minus x square. At origin f of 0, 0 is 0, and on the positive x-axis, that is when xy is x0, where x greater than 0, we have f of xy is 0 minus x square. So this is less than 0. Now we consider a point very much near to origin on y-axis. Consider a point on y-axis near origin. That is, for epsilon positive, y belongs to 0 epsilon on y-axis. So y-axis is like this. So this is the origin, and suppose that this is an epsilon positive, so y is chosen to be here. Then we have y raised to 4 is less than y square for this y in 0 epsilon. Therefore, f of xy is y square minus y raised to 4 minus x square. So this is equal to y square minus y raised to 4 minus 0, since on y axis x is 0. So clearly this is greater than 0, since y raised to 4 is less than y square. That is, there exists a point near origin at which f of xy is greater than f of 0, 0, that is equal to 0, and f of xy less than f of 0, 0, that is equal to 0. Therefore, 0, 0, f of 0, 0, that is equal to 0, 0, 0 is a saddle point. To the surface, z is equal to y square minus y raised to 4 minus x square. The first derivative test for local extreme values says that the only points where a function f of xy can assume extreme values are critical points and boundary points. As with differentiable functions of a single variable, not every critical point gives rise to a local extremum. A differentiable function of a single variable might have a point of inflection. A differentiable function of two variables might have a saddle point. Not every critical points are extreme points. They may be saddle points also in case of functions of two variables. Now we do a problem. So find the local extreme values, if exist, of the function f of xy is equal to y square minus x square. We have the domain is the entire xy plane, so it has no boundary points. So we have fx equal to minus 2x and fy is equal to 2y. Therefore, fx equal to 0 implies minus 2x equal to 0. So this implies x equal to 0. And fy equal to 0 implies 2y equal to 0. So this implies y equal to 0. Therefore, origin is the only critical point because the domain of the function is the entire xy plane. Therefore, origin 0, 0 is the critical point. Now, along positive x-axis, f of x0, this is equal to pi square minus x square. This is equal to 0 minus x square. So this is negative. And along positive y-axis, f of 0y, this is equal to y square minus 0. So this is greater than 0. Therefore, in the neighborhood of 0, 0, there are points at which f of xy is greater than f of 0, 0, that is equal to 0, and f of xy is less than f of 0, 0, that is 0. Therefore, 0, 0 is a saddle point. Therefore 0 0 f of 0 0, that is equal to 0 0 0, is a saddle point to the surface z equal to y square minus x square. So origin is a saddle point. Therefore the function has no local extrema. F of xy is equal to y square minus x square has no local extrema. Now you can verify all these things using GeoGebra. So this is the surface. You can see that origin is a saddle point because f of xy is positive or negative near origin. So you can see that in the neighborhood of origin there are points at which f of xy is greater than 0. So this f of xy is greater than 0 here, and there are points near origin at which f of xy is less than 0. So this is that surface. Now you can have some homeworks. So using first derivative test, you find the local maxima, local minima and saddle points to the following functions. You try it using first derivative test, and we will discuss the second derivative test in the next class. So that's all for today. Have a nice day.